Then it's my pleasure to welcome you to data warehouses and data mining. And today we will talk about querying. So we will talk about what these OLAP operations, online analytical processing, actually is about. And we will talk about the additional operations that we need to complement what we have in SQL already. We will talk about implementations of that, so there is an extension of SQL, but we will also talk about dialects, or one dialect that is very common, MDX, which is a Microsoft dialect. But basically the point of today's lecture is to show you some of the operations that are necessary. So as we already saw, big data is the central focus of data warehousing. So we have a lot of data, and that means if we have a query and we want to compare the data or aggregate the data, we also have big queries. So we have queries with long run times. We usually have queries that do only reads on the data, however, that read a large portion of the data, so that may actually do multiple scans over the data, which is especially true for data mining queries later on. So what we need to do to speed up these queries, to make this kind of interactive search behavior of the data analyst possible, is we need some redundancy, we need some pre-aggregated results, so materialized views, special purpose indices are a definite must, right? So we want it to be as quickly as possible. In the best case, you have the information at your fingertips, and whatever you query will immediately show up and not in a report 4 hours later, right? So sometimes it cannot be helped, but still. The data is reasonably fresh, so in data warehouses it might be stale, but only kind of a day old or a week old, depending on how you feed your data warehouse. The ETL process to feed the data warehouse will be in next week's lecture. And the basic idea now, what to do with the data, is exactly online analytical processing, or for short, OLAP, right? And so this is what we are going to do today. OLAP is used in many areas. The classical job title that you have when you really use OLAP is the business analyst, right, or data analyst. And many companies these days have put IT on a top executive board level. So, for example, if you look at the Volkswagen Financial Services that we have here, they actually have an executive that is only responsible for IT, which shows you what the basic value of IT is in many businesses these days. If you don't have good data, the decisions of your management will suck, right? So we're talking about decision support for management information, but also for other areas where a lot of data is collected, government, for example. So you need to know everything about what's going on in government to make good decisions, and also to give the transparency to users, right, or to citizens. There's a large movement recently that calls for transparency, in that all the protocols and all the decisions are kind of publicly announced. If you cannot search that, if you cannot evaluate that, right, there's no transparency whatsoever. So you need tools there. And finally, there's scientific databases, for example, geo or bioinformatics come to mind. So when you have all these pharmaceutical companies that try docking, that try drug design, and want to know which molecules that could be used as as medicine later on, dock to which receptors in the cell, in the body, right? And then might have what effects. That is one thing. Scientific database is one of the biggest one. Was at CERN, the Large Hadron Collider, when they were looking for the Higgs boson. So that's a lot of data. I mean, when the Large Hadron Collider ran, it produced 120 terabyte per day, and that is just the experimental data. So you can see that's quite a lot. It doesn't sound too much, but if you have to handle it, if you have to manage it, and if you have to search for kind of the needle in the haystack, right, then it is a lot of data. And you want response time that are kind of couple of seconds, couple of minutes, but not in the range of hours, right? So this classical, there are some reports that are overarching, right, and that need a lot of joins and that kind of like show you a lot, that can run overnight. But usually if your boss asks you, you know, like, okay, so how are the sales in North America doing? Then you should be able to get an answer, you know, like in 5 minutes, 10 minutes, but not, you know, like, oh, I can tell you next week. That's kind of not what your boss would expect. So there are some typical OLAP operations, and as we already well saw in the design of the data warehouse, at the base of every data warehouse, there's the cube structure, right? Where you have the different dimensions in the cube that might be locations, products, customer, whatever, right? Whatever dimensions you chose. And within all these little boxes, the cells of the cube, you will find the measures. You will find the entries from the fact table. And then you can say, okay, at, I don't know, this point in time for this product, for this location, we sold so and so many units of whatever it was, right? And then there's, I don't know, 105 or something like that. But there might be more entries in that. Depends on how many measures you actually have. So it might be records in there. That is the cube. And typical OLAP operations will work on this cube. There are classical operations like roll up, drill down, slice, dice, and pivot. But there are also some more complex operations. So the first four operations are basically for navigating the cube. But there are also operations like aggregate functions, ranking, drill across, drill through, that are used for actually exploiting the data, right? And we will go through them and look at each individual function. So let's start with the roll-up, or since the opposite of roll-up is drill down, some people call it drill up and roll down, but doesn't matter. The important difference is up and down. Right, so what can it mean? When designing the cube, we introduced two new ideas basically to classical ER modeling. One was, first one was, what did we introduce more than ER modeling? No idea? A fact table, right? So we had a fact table. And the second one was? Who wants to do the exam? I see. Okay, so we can cancel it. Nobody wants to, obviously. Well, hierarchies. We had dimensional hierarchies, right? So we could kind of like have data on day level, on a daily level, on a weekly level, on a monthly level, aggregate per year, and so on, right? And this is exactly what roll-up does. So it looks at the aggregation level that we're currently on, that the query is currently working on, and does further aggregation, so it moves up the hierarchy, right? And there are two ways of doing an aggregation. You can either move up the hierarchy and say, okay, I have monthly data and I want yearly data, so I kind of like collect all the months of a year and sum it up. Or I can drop entire dimensions and just say, okay, I had my data kind of like by year, by location, and by product, right? And now I don't care about the individual product anymore, any product, I just want year and location. So what did North America sell last year, right? Then I drop the whole product dimension. Both are called roll-up. And of course, you can freely mix them. They're orthogonal to each other. A typical hierarchical roll-up would be kind of that you take the fact table, so it's already right, and some dimension table. So we have the fact table here, and some dimension table. For example, here the product group, right? And you just kind of skip the article, the individual article, and directly work on product group. So you aggregate all the articles that belong to some product group, and you don't do, I don't know, like flat screens and TV sets and whatnot anymore, but you do consumer electronics, right? And all the data of the TV sets and is just summed up to form consumer electronics. Same if you have the time hierarchy and you have daily data, you might say, well, I don't want daily data, I want it per quarter, so I just skip the first two levels and roll up to the dimension, to the aggregation of quarterly information, right? So basically that sums up the days of the month and sums up the months of the quarter, and then you get the value, the combined value, the summed up value here. So those are hierarchical roll-ups. Dimensional roll-ups are even simpler in a way, because what you do is basically when you have your fact table and you had all your data by day, by article, by store, and by client, by the customer, right? Then you can just say, okay, I don't want it per individual customer anymore. Just sum up all the customers in a certain location, right? And then you just drop the dimension. You don't know about the customer anymore. You get an aggregation over all customers in that location for that article at that day, right? So this is a hierarchical roll-up, dimensional roll-up. You just skip whole dimension. When you go up the hierarchy, the question is, of course, how far can you go? And there's one node that we always kind of like looked at as being something special, the apex node, right? Where everything is aggregated into one big number that characterizes your business rather artificially, you know, like you get this one number, 42 or whatever it may be, you know, like, and that tells you everything you need to know about the business. This is usually not sensible, right? But what you actually do is when you look at the different levels, right? You have article, product groups, product families, and then the apex node with the all, right? When you go all the way to the apex, it's basically a dimensional roll-up because you don't care for that dimension anymore. Everything is integrated along this dimension into one big number, right? Everything is summed up. So a hierarchical roll-up that goes all the way to the top can be viewed as a dimensional roll-up that skips the whole dimension, right? Exactly the same. Good? Okay. The opposite of roll-up is drill down, or some people say roll down, right? And the idea is that you de-aggregate the data that you just had. You had monthly data. You want to look a little bit deeper into it and see, okay, so were there certain days that were difficult? So how about the weekends? Did they slump at the weekends, or when are they actually making their business? Or you have location data and say, okay, North America is not doing well. What is it? Is it the rural areas? Is it the cities, right? And what cities? So do our products sell in California, or do they sell on the East Coast and stuff like that, right? So you look at the data, you notice that something is fishy, that something is not like you expected, and then you drill down, you go deeper into the data to get more insight, to collect more insight, right? So it's a deaggregation that takes sums of levels apart. You move from a higher level of the summary to the lower level, right? If, of course, you have a lower level. So if you store monthly data in your data warehouse, then you cannot expect a drill down operation to get you down to daily data, because you're missing the database, right? It could just be guesswork. It could just, distribute it evenly or whatever, right? That doesn't work. So the idea is really that you have either a dimensional drill down where you add a new dimension and say, okay, now I want it also not only the sales in North America, but also per product group, right? New dimension, split data. Or, yes, the sales in North America, but do it by state, right? I want to see California, I want to see New York, I want to see Georgia or something like that. And this would introduce a finer granularity if it exists. Example for the drill down. So for example, here we have 3 shops, and we have time dimension. So this is the time dimension over here, and this is like shops. Yeah, this is like shops. So you can say, okay, I'm owning 3 shops, Joe's, Salitos, and Roots, right? And I can see what they actually do. So let's roll it up and see what I earned each week. Then you build the sum over all these numbers and just get the sums per week, right? So that would be a roll-up by bar. What kind of roll-up is that? Yes? That's a dimensional roll-up because I'm skipping the shop dimension, right? And now I say, okay, well, it seems we have different brands of drinks that are sold in the shops, right? It seems we have a little slump here in the middle, so let's see what's behind that, right? I want to see what we actually sold. So I make up the product dimension. Product. This is still time, right? This was also time. I make up the product dimension, so this is again a dimensional drill down, and now I can see the individual numbers per product. Unnecessary to say, the sum of these numbers is exactly that, right? So this sum is that, and this sum is that. It's no different how I turn the data. The aggregations in the end will always be the same, right? Clear what a drill down and what a roll-up is, right? New query operator, OLAP, very important when you investigate your data. Okay. Those were the 2 operators that actually worked on the hierarchy levels that we introduced. Of course, there are also operators that work on the fact table, that work on the actual cube, and these are slice and dice operators. So what is a slice operator? A slice is a subset of the cube, so that for any of the dimensions you project to a single value, right? And the rest of the dimensions can be either complete or also projected. Right? So you could say, okay, let's project on a certain store, right? And the times from values corresponding to laptops and product dimensions. What you basically do is you do a projection. This is what I'm interested in. And you do a certain selection, so the article has to be a laptop, for example. And this is your good old fact table, right? So slices just mean that you're projecting different, or slicing just means that you're projecting the data in your cube to a single value. To show you how it works on the cube, and since my 3D painting is not too good, this is what it actually does. So I fix a value, laptops here, by some selection, right? And then I project the data with respect to that selection, right? So this is the projection on the other axis, on the other dimension. So I slice a part out of the cube, right? And the idea that I can look at different slices of the data helps me where? Why should I do that? Why is slicing such an important operation? Yes?
Well, if I want to focus on some marketing campaign or something like that, that has to do with laptops, in that case I don't have to look all the other data. That's
right, yeah, you just project the other data away. But more than that, why do I have really slicing? I mean, I could do it with selections and projections, right? So why do I introduce the slicing? That's to save time on queries, not really, because internally it's kind of like reproduced to be a projection and selection.
Reduce complexity.
To reduce complexity for what?
For analyze.
Yes, because?
Because in the info cube you have so many dimensions, you want to reduce something.
Exactly, that is the point. So if you are plotting a visualization of the data for your boss, in how many dimensions are you going to do that? 2 dimensions, right? See what a slice does? It gets you a 2-dimensional view through the cube, right? So you can immediately plot these numbers in different diagrams. For each measure you get a diagram that is 2-dimensional, here with geography and time and the number of laptops, right? And then you can either slice for different product groups or whatever you want, right? But this is exactly the idea of a slice. Since you usually analyze things in lower dimensionalities, you slice them out. Okay, slicing is one thing. You get all the data nicely projected and selected. But sometimes you're not interested in the whole data of the cube, but you're interested in very particular areas. Especially what is important in data warehouses are range queries, right? So you want all the data between a certain time and a certain last, ranging from the 1st of February to the 1st of May or the 15th of May for some reason, right? So these typical range queries where you take a certain time range or a certain geographic range or a certain range of products or whatever it is. And also for that we have a operation which is called dice. So the dice is a range select condition on one dimension or equality select on more than one dimensions. And what you cut out is parts of the cube, bigger blocks of the cube. Might also be that you kind of like only cut out those, right? So you do a range select on the cube and find something out, for example, laptop and cell phone or something like that, and project away, so aggregate all the other data, right? Slice is a simple slice through the cake, right? So through the cube, you just get a complete spreadsheet of what you're looking at. Dicing allows you to get smaller cubes, right? Note that these cubes are not two-dimensional anymore, right? Or not really down to a number of dimensions. So you might still have to slice them to find out the individual layers that you're interested in, right? So that is one possibility of slicing, the dimensional slicing. The other one would be range queries on several areas. So, for example, here we have the article ID is laptop and the month ID is December, and that slices out a much smaller area in my cube, right? So that's just basically a row in the cube. Dicing allows me arbitrary pieces of the cube. Slicing just slices through. Clear what slicing and dicing does? Right. So, good. Then we have pivot. Pivot is not actually a selection or projection operation. Pivot is just for showing data in different ways, because the way that the cube is arranged, right, the way that you arrange your dimension is arbitrary, right? At some point, the designer says, okay, we have 4 dimensions. The first one is product, the second one is time, the third one is location, or something like that. And when you slice through it, right, you automatically get the array of dimensions that the designer of the cube set for you. Maybe you need it in a different way around. So you don't want time by shop, but you want shop by time, right? So for showing the thing. This is actually what a pivot does, or some people also say rotate, because you rotate the axis. Nothing happens to the data, but you just rotate the axis. And a pivot is just for exchanging these axes with each other. So usually when you take data out of the cube by a slice, for example, you get something that resembles an Excel spreadsheet, and this is for deeper investigations. This is for showing the people in the executive board making nice graphs from that, right? And the result of pivot is just you change the axis in the cross table. So, for example, if you have flop a location dimension and a time dimension on a sales table, right? So they are kind of like, here's the city ID that is kind of tied to the city ID here, and there's the time ID that is tied to the time ID here, and the measure that you have is the amount of what was actually sold, right? Then you can show the amount by time and location, right? And if you do that, you might just take a slice, flip, pivoting on city and day, for example. So you kind of like bring it down to city and day. And then you know how many units were sold, for example, in Hamburg on Monday, or in, I don't know, Hannover on Thursday or something like that, right? And you get the subtotals, which is just, you know, like the sums of the columns and the rows, and then you get the apex, which is basically a double sum, right? And this is a slice of the cake. This is what you got, right? And now you might be interested in kind of having it showing it in a different way. So you say pivot, and what pivot does, it just replaces, it rotates those two axes. So you have the time axis here, you had the location axis here, now you have the location axis here, and the time axis here. Okay? This is all it does. So just pivoting things around to show them in a better way or make them fit for your presentation, so it fits the sheet better, or I don't know, right? So just changing the axis. Okay. The numbers, of course, stay the same, right? So if something was 540 here, it will, after pivoting, still be 540, right? You don't change the numbers. You don't change anything. You don't aggregate anything, right? This is not what pivoting does. Whoop. Okay. Those were the base extensions that you have in OLAP database queries: roll up, drill down, slice, dice, and pivot. Right? 5 operations that are basically in all on the heart of all data warehousing systems. Now you get some more, because the analysis of data does not only need to kind of like select the right data or project dimensions away or something, but it also needs a statistical investigation of the data, right? And you know that many of the things can be done in SQL. So sometimes in the SQL lab, I pose the query, okay, can you calculate the median of some data set in SQL? Right? And there's no function for median, right? So there's no inbuilt function. What do? Right? You basically look at the number of objects in the table. So you find out by a count statement how many there are. Then you sort them. Then you kind of like move the rows until you are at half of the total table size. This is the median, right? So you can get it out by SQL. But consider it, you know, like it will not really be nice for the analyst to kind of like write statements. And we've seen some of the OLAP statements that can grow very big and include a lot of joins, and you need to know exactly what you do, right? So that's kind of difficult sometimes. So what is usually done in data warehouses for the business analysis, or to make the job of the business analysis a little bit easier, is not only to allow the business analysis to pose SQL queries and to go into all these pivoting and slicing, dicing, and so on a console level, right, where you just have to write the code, but to do it through specialized graphical user interfaces, right? And this is one of the issues that is called OLAP data visualization, and this is one of the issues where a lot of money is made, not only by really working with the data warehouse, working with the basic functionality, but serving as an intermediary between the analyst on one side and the data warehouse on the other side. And who has ever installed a database? Okay, very few. Who has done it via console? No? If you did it once, right, you will know what a data administrator job is like, and you will probably never do it again. So what we are doing now is kind of like look at some of the visualizations that allow a little bit more easy access.
Right, so in the detour today we're going to look at some of the business intelligence platforms out there for data warehousing that gives you this rather intuitive interface that you can easily work with, and rather than writing your own SQL statements. And one of the famous ones is Crystal Designs, which was initially inquired in 2003 by Business Objects, which was then as well then inquired by SAP in 2008. And very easily, if we just at the very beginning start by a normal two-dimensional representation of our data. As you might all expect, that's very easy to represent. That would probably boil down to a single table, where here, for instance, you have the product dimension, the store dimension, and you basically want to see the sales of each store by their products. And then you get here the measures, which could be the number of items sold, and the stores are here, and the dimensions are on the other side. So this is very easy and not characteristic of crystal designs. As you would expect, if you go up to higher levels, it will start to get tricky. And to visualize 3 dimensions, 4 dimensions, up to n dimensions, there are basically 2 solutions out there. The first one is called layering. And the layering works a little bit like our Excel sheets, where you have the different spreadsheets. And basically, you have them at the back of each other, and you toggle between them. Up to 3 dimension, it is doable, because what you have to do here, they're all on your screen. However, you have to toggle manually between them, and then you have to probably do some joins with your eyes and connect some things on your own. If you go up to higher levels, layering might be a little bit tricky to do. So another solution is so-called nesting. And what you do with nesting is that you start introducing some redundancy in your table, like the measures here, and you start nesting them within each store. So here, as before, we had the product dimension, we had the store dimension, and we introduce different measures. We don't only want one measure, so introduce the revenue and the cost, and this is basically nested for every store. And then you have these little nestings over here. You can also add a 4th dimension over here, which is the days, and this basically acts like a filter. So here it's set to Monday. If you put it to Tuesday, then the whole thing will refresh. So this, the days here is a little bit like the layering concept. It shows you things more clearly maybe than the layering, but again, 4 or 5 dimensions is okay. Going up to higher dimensions, usually difficult to see. So a rule of thumb, usually look at 4 or 5 dimensions. More than that, it's hard to really see, to really capture any information or any insight from the data. One of the basic requirements or applications that OLAP platforms or programs provide is that they are web-based, because most of the platforms, also the tabs out there now, they support web applications. So it's more than feasible or easier to work with them. It's actually a very practical solution. And one of those is the IBM Infosphere. And you get then this normal web-based interface, and if you want to produce a report, for instance, how does the environment look here? Well, basically here you get the final report that you want, and then you start on the size to identify the dimensions that you would want to include, and the measures as well. And this report that was produced here, you basically then set as well which year you want, which broadcast you want, what's the product name, which quarter, and then you hit the run button over here, and you get a nice report on this side. So pretty easy and to work with through the console, which is exactly their target. We've seen so far some of the special cube operations. So for instance, the drill down. How can that be done when you're working through an interface like that? Well, very easy. You basically just go into drop menus. So if we want to drill down in the time period, you just go to the drop down menu over here, and then you have year, quarter, month, and you drill down, of course, up to the point where the data is stored in your data warehouse. So if the month was the smallest granularity that you have in your data warehouse, you won't find here days, because that's not going to materialize itself out of thin air. So this represents the data that is underneath. And then, of course, what you can also do after you choose the drill down operation, you can say what's the sorting order that you want to do, ascendingly or descendingly, limit of the output. You can really play around, just visualize your data the way you want it to look like and produce a report as you see fit. Something else that you can do is visualizations and creating graphs. And you'll see here they are not really very impressive because the idea is we're still talking about web interfaces, and they want to use libraries that are basically compatible with different web interfaces. But still, you could always see some trends. So for instance here, this is the report we generated from the previous web interface. We have for each quarter the store names. And for each store name, you have some kind of nesting that we did. So for the product type, you have analog and digital. These are kind of like nested here. And then you could see here, for instance, that, well, it looks like, let me do this black, a little bit. Digital seems to be selling more most of the time. So this is something that you might see when you start looking at trends. Lastly, one of the rather interesting technologies out there is the interface that was produced or developed by Pablo Technologies, because what they did was they saw what the people, well, who are our users anyway? These people, when they started looking at them, well, they are already very proficient with Excel sheet. They've always been working with, they are very comfortable in this environment, and they know exactly how it works. So they thought, well, why not just put a data warehouse interface and integrate it into Excel sheets, so it just sits on top. And then you basically exploit the fact that people are very familiar with Excel. So what they do is then you identify the cube through a web interface, very easily over here, and then you get the typical Excel sheet, and you can do everything that you've always done with Excel sheet, and you can then get all these nice visualizations that Excel sheet basically provide you with. And this always actually works. Just look what the people in your field are doing and comfortable with, and just give them exactly that. Good? So, from presentation to data.
Okay. So, now we saw that there are actually some very nice tools that allow you a good presentation of the data and how you can easily integrate them into your normal working environments like Excel, where you usually do the graph for the management, right? Because management is kind of like, what do you call it in data analysis? KIF-Niveau, Kinder, Idioten, Vorstände. So you kind of like bring it down, you boil it down to a simple Excel graph that everybody can understand, and where's a clear trend visible that makes your basic argument, and you can say, okay, we have to do something, because if it goes on like that, it will be very good or it will be very bad, depending on what it shows, right? So if you remember the data warehousing architecture that we had, we were talking about different kind of databases, data storage, either integrated with the OLAP interface or on their own. So basically the presentation layer is only on top of that. And we either have a native multidimensional storage, or we have a classical RDBMS-like storage in tables like we know it from RDB1, or we have a mixture where part of it is in tables and another part of it is in multidimensional format, usually on a different level. Usually the aggregated values are multidimensional. The base data is stored in the RDBMS, and we do have different names for that. So if we talk about relational implementations, we usually talk about, I should use the red, we usually talk about roll-up for relational OLAP. If we talk about multidimensional storage, we usually call it MOLAP for multidimensional OLAP, and if we talk about a mixture of the two, we usually call it HOLAP for hybrid OLAP, yeah, because we use both technologies. Okay, So this was the basic data warehousing architecture, underlying storage technology, the server on top, and then we have the presentation usually on the client side. So we have a typical client-server architecture here. Client-server, the client displays the reports, allows for the interaction with the data, and then you send it to the server, to the data warehousing server, and the data warehousing server will deal with all the OLAP operations, right? And it really depends on what kind of model you're using. So if you use MOLAP, ROLAP, or HOLAP, because of course you're trying to reuse much of the existing technology, right? If you have a complete relational database server, not letting that server do all the nice optimizations that they have been built for, right? All the queries that they are very good at would be a waste. You know, like doing that in middleware or doing that on the client side does not make any sense. On the other hand, if you have multidimensional data stored somewhere in the HOLAP server, right, then doing the queries there is not a bad thing. So that could be actually moved to the client side. So if you have an OLAP server, you usually have a high-capacity multi-user data manipulation engine that is designed to support and operate multidimensional data structures, right? And the basic idea is that this server is only responsible for answering business analytical queries. It has nothing to do with the current, you know, like transactional business, and usually it does not serve any other things like the web server or whatever, right? You try to use a fast and dedicated machine for that to speed up the process of answering OLAP queries. Okay, so how it does that depends on the actual implementation of how you did it. So if you're using MOLAP, then basically the multidimensional information is physically staged. So you store it in a multidimensional array and can read it directly from that multidimensional array, especially if it all fits in main memory. This is an amazingly efficient way of dealing with data, right? And we will talk about real-time data warehousing in 2 lectures time. So lecture after next will be real-time data warehousing, and we will see some of these tricks there. If you store it in a relational database, you need something in between, the database management system, that kind of simulates the multidimensionality of the data. And it does it with special schemes. We talked about star schemes, we talked about snowflake schemes, right, that show multidimensional data in a relational, that means 2-dimensional way, right? And then just does the connections with the foreign key constraints that you have between the dimension and the fact table. Or you can basically do it both, so a little bit of physical staging with a little bit of simulation if you do hybrid OLAP, if you kind of use both technologies together. Okay, Now the query is, of course, you have these OLAP operations, slicing, dicing, and so on, and now you want to get it through to the data, right? You want the results from the data. And in OLTP and transactional databases, we're always seeing SQL as the structured query language, right? So all the data accesses, all the data manipulation that we do can be done through SQL. So the obvious idea is, if we have a roll-up environment, why don't we just use SQL, right? It's easy, everybody knows how to do that. People learn that in RDB1, right? And then they should be able to do that for the rest of their life. The problem is really that some of the OLAP operations are very difficult to express in SQL. I mean, we had the Walmart example in the first lecture, right, where it was, okay, a simple query, I want to know what the campaign for toothpaste in the Middle Western states or something like that brought in. And then you had to do a 7-fold join over different tables, right, with a lot of selections, and you just can go wrong. So it's really sometimes very hard to express in classical SQL. And we talked about a couple of necessary operations, but the standardization of these operations, what does a roll-up actually do, what kind of like the grouping should be, or how the aggregates are actually built. That has not really been standardized until 1999. So the SQL that we know from traditional databases is SQL 92, right, or SQL2. That is fully implemented, and all the extensions, SQL 99, SQL 2000, so SQL 3 is the current standard, that have been enriched by so many things that I know no single vendor that implemented the full standard, right? So given that the SQL 3 standard has 1,700 pages, right, there would be a lot to implement. And note, everything that you implement in there always sounds easy, you know, like just implement it. Everything that you implement there has to be integrated into your database kernel, has to be integrated into your query optimizer. Touching the query optimizer is a very subtle thing for database vendors, because this is at the heart of what makes them fast, what makes them competitive, right? If they then just say, okay, I introduce pivot or slice and dice or something like that, and then the query optimizer doesn't work because it cannot really work with these or integrate these new commands, right? Then you have a problem. You're kind of like bound to have losses in your sales numbers. So there is no standard query for OLAP. Everybody does what the vendor likes, but there are two choices that you will see quite often. For relational OLAP, there's SQL 99, which was a standardization within the SQL framework, and there's MDX for multidimensional OLAP, and also for rollup, which is kind of like an SQL-like query language that is somewhere between SQL and Excel macros, you know, like, so it fits the bill to some degree, right? And we will talk about both of them for the remainder of this lecture. So let's start with the SQL dialect, right? If you have a typical OLAP queries, then what you do is basically you do a selection somehow. So for example, the region should be Europe. You're talking about groupings, right? So you want to have the data per region, per month, per quarter or something like that. And you're talking about aggregation. So, for example, if you have a sales cube, you might be interested in how many units sold. You might also be interested in how many profit you did with it. And maybe profit after taxes, profit before taxes. And all that is based on the same data, right? And can be aggregated in different forms, right? So you could say the price times the volume is what I have in terms of revenue, right? And then you have a new measure, revenue, that is derived from the old measures, price and volume, right? So can be done. What you do when you transport that into OLAP is, of course, the selections go somewhere into the where condition, right? So I don't know, for example, A is smaller than a certain value, and this is smaller than B, or some field has a value C or whatever, so region is Europe or whatever. You have the group bys that go into the group by statement, right? Where you say, okay, I want it by region, by month, and all these values should be aggregated. And the aggregations usually either go here, so you want the count, you want the sum, however, very limited number of aggregate functions, or they go here into the group by having clauses, right, and there you can also do the counts and different aggregations. So we know where they go basically, but they're very difficult to use for somebody who's not willing to write big statements in SQL. And therefore, the vendors were kind of talking with each other and decided we need something new. When the next SQL standard comes out, there should be some OLAP commands in that. And that should be something for grouping. Oops. That should be something for grouping. That should be something for the roll-up, drill down. And that should be something for slicing and dicing. So they introduced new commands, grouping sets, roll-up, and cube. Moreover, the aggregate function that classic SQL had, right, sum, average, count, are not too impressive in terms of statistics, right? So you don't have a median, very complex to build in SQL. You don't have regression, right? You have none of these wonderful things that you need to show trends, that you need to kind of look at things. You also have a set-based result in SQL, right? So you're all dealing with entire sets, and you cannot say how big these sets will be, right? If you say everything where the region is Europe, then the number of tuples in the database determines the size of your result, right? But what about queries of the type, I want the top three salesmen of the department. I want the best-selling product, right? How are you going to do that? And this is kind of like these top K queries. So the new SQL standard kind of looked at how OLAP query operators could be integrated in normal SQL, looked into new aggregate functions and top K kind of queries, top K type of queries. So let's take a look at SQL 92, so the good old SQL, and see how to do OLAP queries, right? It's very hard to express multiple aggregation in SQL. So what we really want, if you remember those, I have the time here, for example, I have the shop here, for example, right? And then I have the aggregates over time, right? All the shops at a certain point in time. I have the aggregates, each shop all the time, right? And I have the aggregate down here, right? All driven into one number, so all the time, all the shops, right? In one number. A double sum does not work in SQL92. You cannot you cannot nest aggregation operators. That does not work. Computing them is not done automatically by SQL92. So if you kind of like select this data, then you get the pure data. You don't get any aggregates. Also difficult, comparisons between things. So how much units of a certain product did we sell this year and last year, right? You have to build two views and compare between them, right? Or you have to make a self-join to kind of like find out what the respective value was last year, right? And then the reporting features. SQL hardly has any reporting features, right? You can structure the output, right, and kind of like hand it on to a application, but that is that. It does not do anything automatically. Moreover, what happens when you do SQL92, and SQL92 has been built and has been optimized for short duration transactional data processing, right? So update this value, select those values over there, sum up these values, right? That runs really fast in SQL. Complex queries, self-joins with multiple applications do not run fast in SQL. So you really have a certain performance penalty, and the execution of long and difficult queries will be rather long-running because they cannot be optimized sufficiently, right? Finally, there's a lack of statistical functions. I just said, you know, like sum, count, average, and that's about it. Min, max, right? That's about what you have. You don't have any of the more complex functions. So let's look at the individual things. How would you do some of the things that we're talking about in SQL92, right? So for example, if you have multiple aggregations and you need exactly those sums down here, sums up here, right? Sum and the apex sum down here, right? How would you do it? Well, first you need to select this. Okay, this is simple. Select model, make, sum amount from sales, group by model, make, right? Gives you this box over here. Then you need the two aggregations by each individual row or column, right? So those two over here are those here. One group by model, one group by made, right? And you get the aggregation. Finally, we're talking about the apex. Down here, you sum up everything from the sales table, right? You see, this is a fourfold union of individual queries to get what we get in an OLAP spreadsheet, right? Very complex to do. Could that be easier in SQL? Yes, and this is why they provided new operators. Okay, let's look at the second case. We want to do comparisons. We want to do comparisons in SQL, right? So for example, this year's sales against last year's sales for each product. What do you have to do? Well, basically you have to rely on a self-join. So for the products, we kind of like create a view that selects the summed up quantity per year per product idea, right? Grouped by the product ID and the year. So now we have for each year an entry where the aggregation is already made. How can we now compare last year and this year? Well, basically, we have to do a self-join between well, the current sales values and last year's sales values, where the product ID is exactly the same, right? So this is a join between V sales and V sales, zack, where product ID is the same, right? Product ID is the same, right? And then we can say, okay, current year is last year plus 1, so we get adjacent years. Kind of tricky to do, right? So question, can that be made easier? And answer, yes, but only by new operators in classical SQL. Good. Then reporting features in SQL 92 are much too complex to express. So for example, you don't have any ranking aggregation. Since everything is set-based in SQL, you don't have a special ordering on the result set. Also typical questions, entiles. I want the quantiles, I want the quartiles, first quartile or something like that, the first 20% of products or something like that, medians, moving averages, cumulative values, all do not exist in classical SQL, right? So for example, if you want to build a moving average over a 3-day window, what you have to do is, again, create a view that takes all the different windows, right? And then what you do is kind of like you do a self-join over that view, where you provide the start date and the end date for your window, and then look at the end time and the start time of every item. Make sure that they are 3 days apart, right, grouped by the end time. And then you can average up the sums. So this is how you build three-day moving averages, right? So you build a view, then you do a self-join that does the 3-day windows by taking always dates that are 2 days apart, right? And then you aggregate them manually. I mean, you all know SQL, you all heard RDB1. Who would have thought of that query immediately? For such a simple thing as a 3-day moving average, right? You sum up the value of 3 days and you divide it by 3. Does not sound too difficult, right? So conceptually, it's very simple, right? But in SQL, it's kind of a little bit clumsy, to say the least. And this is why there were more functions integrated into SQL 92, and we will look at some of the OLAP functions in the next detour.
So as we've seen in the previous slide, doing something like moving averages, it's doable. However, it's not very intuitive. You can't quickly think of it, and it's rather difficult to write. So you had to create this view, and you had to do self-joins. And there's a lot of other things, as we've said, that is rather complicated to do with SQL 92. And that's why when they created the SQL 99, well, they thought of these, let's call them shortcomings, and they tried to introduce new operators, new clauses that would make life simpler, that would make things easier to get these results. And the basic clause that I'll talk about in this detour is the window clause. And the window clause, you can do a lot of things with it. You can do moving averages, you can do ranking with it, as we will see. And the window clause, basically what it allows you is to create some kind of a dynamic window. And you decide on the size of the window, you decide how it's sorted, and what kind of aggregations that you can do on top of it. As an example for that, how can you write the window clause? Basically, you break it down into 3 different sub-clauses. The first clause is the partitioning, ordering, and then aggregation grouping. In the partitioning, you basically identify which rows you're going to work with. Are you going to only be looking at the products? Are you going to be looking at the time? Are you going to be looking at the shops that you have? And then comes the ordering subclause. And the ordering is you enforce some ordering. But the key thing here is the ordering that you enforce is not on your entire data. However, the ordering is enforced within each partition. So every partition has its own order. Whenever you go to a new partition, the order starts again. And lastly, the aggregation grouping. Here you identify which aggregation you want to do and on which sets of rows. So how can we actually use the window clause to solve something like the moving average, which we just saw 2 slides ago? Well, basically all we need to do is, let's assume we want to get a moving average on our sales. So you select the average of the sales, and then the syntax here for the window clause is basically over, partition by, order by, and then the aggregation grouping comes later. So you say, okay, I'm going to partition by the region. I want to see the sales by region. So it creates partition by the region. And within each region, you start ordering here by the month. So from January till December or so. And then comes the aggregation grouping. And here is the trick for the moving average. So you identify the set of rows that you're going to be working on which this aggregation function work. And this is the current row plus the 2 rows that are preceding the current row. And this means then that you're basically working with 3. So a moving average of 3 rows. If you wanted a moving average of 4 rows, then would it be rows 3 preceding. And the higher you want your moving averages, the higher you can set this number. And it is so simple, you can actually then try different window sizes and see how the averages differs, how the influences in the sales differ. Maybe if there was a huge sale in December because of Christmas, you can either downside this influence or actually make it bigger and see its impact. The second operation that you can do with the window clause is ranking. Ranking is basically you give an order to the result set that is coming out from your SQL query, and it's a very basic operation. And the old style that you usually had from the row numbering was basically you get your results over here and you just do a running count and it just incrementally go up higher in number. So here if we're selecting the sales order ID, the customer ID, and we enforce an order by the sales order ID, and then we set some condition, you get the running count on these sales order ID. Pretty simple, straightforward, nothing tricky here, right? The only thing that might be problematic is that this kind of ranking function is not deterministic. What does that mean? It means we set our order in the previous SQL statement to order according to the sales order ID. And it might happen that you have 2 tuples that produce 2 regions that produce the same sales. And what happens here is, one time you run the SQL statement, the first region was ranked 1, second region was ranked 2, second. If you rerun the SQL again, they might switch. And this is why we call it non-deterministic. So to get over that, there are 2 different functions that were introduced in SQL 99, the rank and the dense rank. And again, they work with the window clause that we've been talking about. And you have 2 different possibilities that you can actually produce by the syntax. The syntax is as follows: rank over, you identify the partition and the order clause. So this means you can either, this is not mandatory, you can either rank, you give an order on all the data that you have, or you can identify a partition and enforce the order on each partition. So let's see what's the difference between these two functions in the simplest form, where you actually enforce the order on all the data that you have and not within each partition. So, for example, here we have select channel, calendar, and we aggregated the sales here, summation, and here we start ranking the normal rank and the dense rank. So the two new functions that I've been talking about. And what do they do? Well, let's have a look. They're supposed to be now deterministic. So if you notice here, because that was actually our problem 3 slides ago, that is when you have the sales and the sales are equal for 2 different products for 2 different channels here, 2 different calendar dates. The ranking function, what it does is it leaves gaps in the ranking. It means as soon as you have 2 equal sales, then they're both ranked 3rd. So we don't have 3rd and 4th as before. They both take the same ranking. However, the next channel that comes into play, that comes next, it's not given rank 4, it's given rank 5. Because this is actually, it basically is holding up the places for the 3rd and the 4th rank. This is the rank. The dense rank, well, it leaves no gaps. This means, again, they both have rank 3, but this now gets rank 4. Ranking might be a little bit problematic if you have a script that you've already run that doesn't take into account that there might be a gap here. Then you might get runtime error. Really depends what you want to do. But you have these 2 possibilities or solutions, and you choose which one to use according to your needs. Now, the second thing that you can do with the rank function is to use the partitioning clause that is also available for you to use. And this means that you identify the partition, you partition by region, you partition by product, whatever it is, and then you enforce the orders within this partition. So the rank gets reset every time the new partition starts. So if we look at the example that we just had before, but now we're actually using partitioning. So we're using the ranking, and now we partition by the channel. This means this is one partition, this is another partition, and this is the 3rd one. What happens here? Before, when we didn't do the partitioning, the order was enforced on all of these channels. So you had 1, 2, 3, 3, and 5. Here, what happens is you start getting the ranking within each partition. So in the direct sales, 10,000, 9,000, they are ranked normally 1, 2. In the internet channel, both of them had sales of 6,000, so they both tie up at rank 1, and the partners tie up, well, there's only one, so it has ranking of 1. So this basically, as soon as you identify the partition, you can then enforce the order within the different groups and see then who has the best sales in the channel of direct sales or internet. Good. One last thing that I will be introducing for the SQL99 is basically doing the end-tiles. And yeah, it's basically not part of the standard, but most of the major vendors adopted or integrated it into their underlying SQL. So what happens, what does an end-tile basically do? Well, basically it creates buckets, and it divides your data in a sorted manner into these buckets, and the key thing is it tries to create these buckets such that they are equal in size. Of course, if you have an even number of tuples, all of the buckets will be the same size, except one of them will have one extra tuple. But usually you try, that's going to be the maximum difference. One bucket will have one tuple that is more. And this can actually then be used for also top K queries. If you want to look at the top shops that are selling products or the best regions that you have, you can do that with n tiles. So how is that done? Well, you basically specify how many buckets you want, n tile 3, and what you're going to order by. So we're ordering by the sales, which means that now n tile is 3, so you create 3 buckets, and you're ordering by sales, so you want them to be ordered accordingly. And you'll see now here that the buckets that were created bucket 1, bucket 2, bucket 3, so all of them are the same size except here. And those who have similar or closer sales are basically grouped together. So they might seem like it's exactly the same table and you basically cut like that, but actually no, had they been shuffled a little bit, then they would have been regrouped like that. So it's basically in a little bit sorted fashion. Popular percentiles that usually are done are the quartile, where you basically have 25% of your data in each bucket, and then they would be 4, or the 100 percentile, you have the 100. Of course, if you specify here n tile n, where n is bigger than the number of tuples that you have, basically you end up with, in each bucket you'll have only one tuple, and this basically acts like a ranking. So like we talked about, just ranking the tuples. Very good. Everyone clear on the window close and how it can be used? Yeah. Okay. So we go to a break now, and then we can talk more about SQL 99 and the different functionalities they provide. Okay, so 10 minutes.
So, dann machen wir mal weiter. So we talked about the statistical operators now and specialized operators, but we still have the problem with the aggregations, right? So the aggregations and the cube structure needs to be targeted, and there's an extension in SQL 99 that is called grouping operators, and they come in 3 flavors: the grouping set, roll-up features, and the cube feature. And let's start with the grouping set. The grouping set replaces the series of union queries that kind of does the aggregation by either of the different dimensions, right? So the interesting thing is that, for example, if you have a spreadsheet that has the job title and the department name, right? So you have departments, 1, 2, 3, 4, 5, and you have job titles, different job titles, and then you want the number of people in these with these job titles per department, right? Then you would need the sums over here and the sums over here, okay? And this is exactly what these queries are about, right? So one groups by department name and counts all the job titles per department name, and the other one groups by job title and counts all the job title for all the department. What you can see here is kind of interesting, since since one of the things is kind of like aggregated, right? So I'm not talking about individual departments anymore. I'm talking about all departments, the sum of all departments. I need null values, right, for the rows. And these null values are kind of generated null values, right? And to write that in classical SQL 92, old SQL, and to simplify it in SQL 99, you introduce a grouping set. And a grouping set means you're not only grouping by these items, but you also compute the aggregations over these different dimensions, right? So the union between this area and this area as given by this query, right, can expressed in SQL 99 by a grouping set. And grouping set means that it's grouped by department name and job title, and for both are individually the aggregations are computed. Okay. I should not write so much on the slides, because then the erasing costs so much time. But okay. The issue with the null values is that you now have two kinds of null values, right? You might have null values in the data, so you don't know a value. But for the aggregates, you create new null values. So, for example, if you do, okay, I have a aggregation from the real data, the quantity of cars sold of different brands per year, right? Then I have the year and the brand and the quantity as the quantity as a measure, right? Then this is the real data, and in my grouping set, I aggregate over all the brands. So this is the sum, right, of these values. But since I now have all the brands, I generate a null value because I cannot put anything in that column. I could write all or something like that, but then I would kind of like find out that all might be the name of something, right? So it's kind of difficult. But I also might have real null values that are just lacking in the data, right? And the question is, how can we distinguish between the two? Between the generated null that are typical signs of aggregation columns or aggregation rows, and the normal null values that are in the data, right? And this is done by the database system. So the database system takes care of the difference, and there's a grouping function call where a 0 is returned for null that is really immanent in the data, and a 1 for a generated null that is only there because something has been aggregated. Okay? Clear how it works? The grouping sets, right? So grouping sets are built on top of group bys and compute the aggregations for all the items in the grouping set. Right? Good. And then for everything that cannot be measured, the generated null value. Then there's a roll-up. A roll-up produces a result set containing the subtotal rows in addition to the regular grouped rows, right? So basically a roll-up means that you build a complete grouping set, by always leaving out the last dimension in the set. So if you have a roll-up ABC and ABC being dimensions, then basically you select the data grouped by ABC, plus you take a grouping set containing ABC, a grouping set containing AB, grouping set containing A, and the apex grouping set, and compute the subtotals. So roll-up does the complete subtotals for that grouping set by always leaving the last one out, right? Until you are basically at the apex. This way of leaving the last one out, of course, is kind of difficult because the order of the grouping set of the roll-up and the order in which you do the roll-up is determining what grouping sets there are. So, for example, if I had said roll-up of CBA, then I get different grouping set. The first one is, of course, the same because it contains everything, but then the last one is left out, so I will get the CB instead of the AB. And that now is a totally different grouping set, right? And then the B is left out, so I will be left with a C instead of the A, right? So you see, order is significant for roll-ups, but basically it just computes all the different grouping sets along these dimensions. How does it work? Well, let's do a sample roll-up operation. So I have the year and brand and the sum of the quantity, how many cars I sold, for example, right? And now I want to do a roll-up by year and brand. So I look at the complete data, then I leave out the brand, and then I leave out the year, right? So I look at the complete data by year and brand. Then I leave out the brand, creates a null, generated null here, right? And gives me only the year. And then I leave out brand and year, which gives me the apex node, right? And I do that for every partition of brand and year. So, for example, I have here all the 2014, all the 2015, and so on models, right? So a roll-up computes all the subtotals for all partitions of the data in the grouping set, plus leaving the last one out, leaving the penultimate out, and so on, until you reach the apex. Clear? So how do I compute, for example, these 1400? Well, I take the quantities from here and here, sum them up, and this is the apex. Everything that has ever been produced. How do I compute the 1000 here? Well, this is by just adding up those, right? Because it's a subtotal of a partition. Okay? Clear what a roll-up does? Good. Finally, so we've done grouping sets, we've done roll-up. Now we could want to compute everything, and that is called the cube operator, right? And the cube operator contains all subtotal roles of a roll-up, and in addition, the cross-tabulation roles, right? So it's a series of grouping set that does all the possible groupings. So, for example, if you have a cube ABC, then you have the grouping set ABC, all two partitions of that grouping set ABC, all single partitions of that grouping set ABC, plus the apex partition, right? So all possibilities of building subtotals, right? If you have the cube, this is why it's called a cube operator, you know, you have all subtotals here, subtotals here, subtotals here, plus subtotals that already do the sides, plus the apex node that kind of aggregates it all to a single row, right? So all possible grouping sets that can be built out of ABC are built by the cube operator. Cool? Grouping sets basically group over the attributes individually that have been built on the that are mentioned in the group by statement. The roll up operator has a sequence of grouping sets where always the last one is left out. The cube operator builds all grouping sets that are possible with all possible subtotals. Right? Good. Let's look at it from a perspective. So if we have the data cube over here, right? Then we have the subtotals per dimension. So these are all the two-dimensional subtotals. We have the subtotals per 2 dimensions. These are those. And we have the subtotals for all dimensions. This is the apex node, right? And we can always kind of like build them out of each other. Right? Everybody understood what it does? So these are grouping sets. One way through the grouping set in a certain order is a roll-up. All of them are the cube operator. Yes? Good. Example, how does it look like? You have the original data partitioned in slices. And now you do all the subtotals that you can do. So you have year branch, then you can do a subtotal by year for each partition. You can do a subtotal by branch for each branch. And you can do the apex node, which is a subtotal by year and branch. Okay? Good. Whee. That should be all for SQL 99. We see a couple of helpful operators that allow you to query far more easily than building these complex SQL 92 queries. But for many people that is not easy enough because they are not working with databases, they are not working in the SQL world, but they are rather working in the Excel world, right? And so Microsoft was among the first to introduce a new query language called MDX, and we are mentioning that because it is still around and you might actually see it. MDX is short for multi-dimensional expressions and is built directly on top of a multi-dimensional storage from Microsoft. It's I usually say it's not really brilliant, right? I mean, it's Microsoft, so it does what it does, right? And it's easy to use, and you know, like you can say what you want about Windows, right? But it's really operable for nearly everybody, right? As opposed to more complex. I mean, yes, Unix might be the better operating system, right? But it's hard to manage sometimes. And this is the same for MDX. Not all data analysts are direct computer science. Many management information people are there, management information systems people. So they should know a bit of SQL, but maybe not so deep. And there are also a lot of economists doing the same job, and they have usually no idea about SQL, and they want something. They can be taught to do something like Visual Basic or C# or something like that. So something that is very very basic, right? And since Microsoft, especially for the kind of middle class business operations, has a lot of market share, many of the OLAP providers, many of the vendors actually adapted to their MDX style of doing multidimensional expression. So it's used in several products. So for example, OLADB is one of the examples, or XML for analysis. It works on multidimensional data stores. It can also work on roll-up, but then it's usually casted into proper SQL. Well, proper SQL basically meaning Microsoft SQL Server or even Access. The MDX basis is something like the SQL syntax, but not so, not so rigid. So what you do is usually you have a select column that gives you the possibility to say what dimensions do you want on columns and on rows. So it kind of like it kind of like mixes the projections with selections already, right? The from clause tells the cube specification, so how you build the cube, right? And if they are joined, data cubes have to share dimensions. So you cannot do implicit joins over the where clause where you say, okay, this argument over here should be this argument or should be equal in value to this argument over there. You can only join different cubes by time, by product, and these must be identical. Otherwise it doesn't work, right? And where basically has only restrictions of the data, so that's kind of the slices and what measures should be returned, right? So it's a slightly easier way of specifying what you actually want, right? Okay, let's look at it. We have some basic elements that can be used. So we have lists. And lists are just enumerations of nodes from different classification level. So you can say something, there's a list with a kind of like set-based bracket, Germany, Niedersachsen, Frankfurt am Main, USA, or something like that. And this is a list of different nodes, right? Don't be concerned about these square brackets. They just mean that the interior of the square bracket is casted to strings. So if it's numbers or if it has blanks in it, right, then it needs to be casted to a string. They do that by that square bracket. It just means it's one expression. It's not Frankfurt am Main, it's Frankfurt am Main, right? So kind of like don't be concerned about the square brackets. Lists are usually done in set brackets. Then you can have different elements that show the roll up and drill down features. So you can, for example, say, I want the children of Germany, which means I drill down to the children of the node Germany, which might be states, Niedersachsen, Bavaria, like Westphalia, and so on. Roll up. I go to the parents. So for example, if I say I have the node Niedersachsen, I want the parent node, that would be Germany. Then I can look at the members of so I can have all the elements of a classification level. So if I say time quarter members, then I get all the months of that quarter, for example, January, February, March, or something like that, right? and they are built. So this is a classical way of traversing nodes, right, by this dot notation, by the path notation, similar to file systems where it's done with a slash, and similar to XML notation where you kind of like use these paths by dots usually. You can also have a functional generation of sets, so not only traversing the node tree, but also functional. So you can say, I want all the descendants of the USA on the level of cities, right? And then you get all the cities that are located in the USA without looking at the states. You can also generate things. So for example, you can build a list that kind of like is put together by some explicit nodes, USA and France, for example, and the descendants of geography current cities, right? So current always means the nodes that I'm looking at, USA and France, so that would enumerate all the cities in USA and France. So with this generate, you can build new lists, you can expand lists from known stuff. Good. Those were lists basically built on the nodes or the node trees. Then you have sets that also are built on the node trees, and basically you nest the set to be able to display more than two dimensions in spreadsheets. So the thing is a cross join. So you're saying Germany, Sachsen, Hannover, Braunschweig, and you're saying IKEA and H&M Möbel on the columns, which kind of like is a nesting of the two dimensions. One is a location dimension, the other one is a store dimension, right? And you basically nest them, right, on columns, and on the rows of the spreadsheet you want to have the childrens of the quarter first and the quarter two. So quarter two stays in an aggregated form. Here the children node breaks it down to January, February, March, right? So you can generate all these different nodes, and then you have the sales cube, and you say which measures you need, right, and what restrictions on the measures should be applied, and then you get the sales number here, right? So what you do with the cross join is basically a nesting of some dimensions into a single dimension. Then you can decide which one should be rows, which one should be columns, right? Where should the data come from, and what data in terms of the measures and in terms of restriction on that data should be shown. Okay, this is the basic feeling of MDX. Finally, we have some special functions. For example, we can have a relative selection that uses the order along the dimensions. So I can, for example, say, okay, in the time dimension, the year of 2014. Again, the square brackets just show a casting into a string of 2014. I want the last child, right? That means I look into the hierarchy, child hierarchy of 2014, which are the quarters, right? And the last child means I want the final quarter, which is last quarter of 2014, quarter 4, right? Or I can have 2014 next member, that will be on the same level as 2014, but one more is 2015, right? 2014, quarter 4, November, lead 2. Lead means always skip ahead. So if I'm in November, skip ahead 2 months, right? November 2014, December 2014, January 2015, it is, right? And finally, there's a short, an abbreviation for intervals, just the colon, and then you get the list of the intervals. So 2010 colon 2014 means from 2010 until 2014, which is 2010, 2011, 2012, 2013, 2014. Okay, just an abbreviation. Okay. Of course, with all these parse expressions where you can navigate up and down the hierarchies, clever for drill downs, clever for roll ups, right? You sometimes need to find out which is the next hierarchy level. And you can ask for that with the level command. So if you say, for example, Germany.level, then it will say, well, the level of Germany is country, right? Or kind of like time, first level is year, second level, quarter, and so on, right? So then you have the brackets. I already explained that. So the set-based brackets is really a set of nodes. Square brackets are basically string casting of numbers, empty spaces, special symbols or something like that, and round brackets are tuples where you build vectors out of things, which is used, for example, for nesting or for like having different measures and different restrictions together, right? The restrictions are done with an AND in the Boolean sense. Okay. Then you have some special functions and filters. So, for example, top count, top percent, or top sum can be used. You select the time children on columns, and the top count, Germany children, 5 sales turnover. That means you get the top 5 children of Germany. Children of Germany are the states, right? So the top 5 performing states in the rows, right? Whatever they may be. Exactly. Then there are some things like, filter functions. So, for example, the areas of Germany with increased turnover, and you can say here, turnover in 2014 must be higher than the turnover in 2015. So you may use arithmetics also in directly in the filter column, right? Good. Finally, there's time series. Sometimes it's for trend analysis and stuff like that. It's kind of clever to have periods or time relevant data. So you can choose time intervals. You could, for example, set periods to date. I want the quarter that contains or until the 15th November of 2014, and the respective quarter would be October, November, December of 2014. So the period in dates would be the 1st of October till the 15th of November, right? So there's always beginning date, end date, and they are matched. They can even be on different granularity. Then there's for self-joins, there's so-called parallel periods. So parallel period year 3, September 2014, goes simply back on the year level of your hierarchy, 3 years, right? So September 2014 is compared to September 2011, right? Parallel period. Of course, parallel periods always lie in the past because you don't have future date, data, right? Okay. There are some more numerical functions used for statistics, covariance, correlation, linear regression, and stuff like that, all built in the system, right? So easy to use. And it's kind of like, you see that it's a little bit more unstructured than SQL, right? You can do a lot of that, and it's kind of like programming Excel macros, right? It reminds very strongly on the shortcuts you do there. And it is exactly that, right? So it has been built in that way, and sometimes it's not clear what the things do, and there are different ways to get to the same aim, but the people working with it understand it very easily. Good. As a last thing in that lecture, I want to introduce MDXML. So this is XML for analysis. It's kind of like a slightly different version of MDX. It's a more recent attempt at standardized application programmer interfaces for OLAP, and basically the sorry for that, off you go. And basically it's built for client applications that can talk to database servers then, right? And everything is XML based, so it has been built for service-oriented infrastructures. You get a wrapper for MDX commands, and the technologies that you use are the typical web service technologies, XML, SOAP, so the Simple Object Application Protocol, and HTTP, so it's all web-based, and you have some service primitives, for example, Discover, where you find out about different data sources or available data scheme, or the execute command, where a web service is invoked that actually performs your MDX query over a service. So this is an exchange format that encapsulates MDX expressions in service-oriented environments. Okay? Good? Questions? SQL 99, MDX? No? Good. Then, what did we do today? What I want you to take home. We talked about typical OLAP queries and what they need. We talked about new kinds of operations. First one was the roll-up and drill-down operations, right? Can be done in hierarchical or dimensional fashion, so you can either go up a level from year to month to day or something like that, or you can just skip a whole dimension, but you can only drill or roll up to where you have the data. You cannot have finer granularities than what is stored in the database. Then we have talked about slicing and dicing. Slicing is basically just projecting data for building spreadsheets for certain values, whereas the dicing is a range query that cuts out part of the cube. Pivoting is just changing or rotating the axis of your spreadsheet, and those are the 5 basic OLAP operations that are needed. Of course, these operations need to be supported by today's databases. We have 2 basic designs of data warehouses. One is the multidimensional design. One is the roll-up design, so the basic data warehouse on top of relational databases. Of course, it was obvious for the roll-up design that you build things like an extension of SQL, which was SQL 99, where you had grouping sets, where you had roll-up and cube operators that allow for an easy computation of the subtotals and of the aggregation values that you need. And you have a lot of different functions that are used for ranking and that are used for statistical computations. Things like moving averages, things like linear regression, and so on. MDX is for the multidimensional part, so it's very similar to the SQL structure, but it's kind of a mixture between the SQL structure and Excel macro queries. You can using parse expressions, you can steer the schema, or you can navigate the schema and get to where you want to. Especially for the multi-dimensional Microsoft product, this is kind of a standard. In OLAP, it's usually mapped to the SQL. And it's very easy to use also in larger business environments when you have service-oriented architectures, because it can be combined with MD-XML, so the multidimensional expressions for XML analysis, and then you have all the different possibilities of web service-based communication to wrap and execute your MDX statement via web service technology. Good? Cool? Okay. And that's for today. Next lecture we are going into actually building the data warehouse. I will show you how to set up the project, and then we will talk about the most important step in building real-world warehouses, which is extract, transform, and load. Central process. Thanks for the attention.